All right. Yeah, I think we can get started then. So today's speaker is Janish. Ryan did his PhD in Berkeley and is now a postdoc at Fermilab, where he's part of the SQMS collaboration. And today he's going to tell us about some new ideas for light shining through wall experiments. So go ahead, Ryan.
Thank you. Yes, thank you all for having me. This has been a lot of fun. And yeah, I would like to tell you about new ideas for doing light shining through walls experiments, specifically with RF technology and pushing that technology to look for heavier mass hidden photons than has been done before. This work is done at Fermilab with Asher Berlin and Ronnie Harnick. So the idea here, the goal is to look for hidden photons. So first, briefly, what are hidden photons? So this is a fairly simple extension of the standard model. So we have, I have to use the band stick. We have a Lagrangian here. So this piece here is familiar. This is just ordinary Maxwell theory. This is a Maxwell massless vector coupled to electromagnetic charge. That's the J. And we want to add to this another abelian vector, which is massive. And then to have something interesting happen, we want this to couple to the standard model in some way. And a very nice, elegant way of doing that is through this kinetic mixing operator. So the new field, the hidden field, doesn't directly interact with charges, but via this operator, it can mix into the regular photon, and which can give us interesting dynamics. So this is a pretty standard idea that's been around for decades. It will be useful to sort of switch back and forth between different bases, right? So we have two fields here. We have our regular photon and our hidden photon. So we can always choose to think about this in terms of different linear combinations of those two fields. And we'll do whatever is most useful for us at a given, problem. So this is a particularly useful basis. So the previous one I'll refer to as the kinetic mixing basis, and this one as the propagation basis. And the idea here is to make this particular transformation. And the point of doing that is it eliminates that kinetic mixing term. So now these two fields are propagation eigenstates. They don't mix with each other at all. And what happens when we make that transformation? So our Maxwell piece stays the same. Our hidden piece, now we have this again, this hidden massive field, but it now picks up a direct coupling two charges in this picture. So in this picture, we sort of just have two copies of electromagnetism. There's the regular one, and then there's this extra one, which is hidden in the sense that the coupling is suppressed by some small number epsilon, and it's massive. So these things could exist, so we should look for them. How would we do that?
Why epsilon equal to 1 gives this trouble?
Why epsilon equal to 1 gives you trouble?
Because it's the forward to the domain.
Yeah. So
I mean, there is a particular reason for this.
is there, I think that this transformation just isn't a sensible one in that limit. That if you go back here and take epsilon equal to 1,
And what is the reason? Yeah, exactly.
you would want to just do a different transformation. I'm not sure. So the reason there, I mean, it's
What is the value of the current in that case? Like when you have this supervisor matrix one,
And then there is
the current is found. And then I guess the question is like, whether if it's is equal to 1, for instance, like, if you have like zero eigenvalue or something,
Yeah.
Actually, one more is not.
yeah, so this is what's happening.
okay. That makes
Yeah,
sense.
and if the diagonal parts are kind of getting bigger and bigger, then you will get 1 minus more.
Yeah. Okay.
This makes sense.
Thank you. Yeah. Okay, so how do we go about looking for this new particle? How do we test if it exists? So if it's, if the coupling was strong enough, you could see it in traditional particle physics experiments and colliders, and people do those searches. But what I want to think about is the regime where, suppose the mass of this hidden photon is quite light, less than an eV, say, and the coupling is very small. in which case you're not going to see this in colliders, but there are other techniques you can use. And a very good idea, which then goes back decades, is the idea of a light shining through walls experiment. And the basic idea here is you take some light source and produce as many photons as you can. You then filter those out with some opaque screen, something that absorbs photons. And if you had no hidden photon in your universe, then this thing would block all the photons. And if you put a detector over here, you would see nothing, right? Light doesn't shine through walls normally. But if you now have this hidden photon in your theory, you have this process, as I've indicated it here, where, in the mixing picture, by paying some price epsilon in your amplitude, a photon can mix into the hidden photon, which then, remember, doesn't interact with charges. So it goes through the wall. It also means it doesn't interact with the detector, but it could mix back, and then you would have a signal. So that's the process you're looking for.
Hidden photon is massless, then this process will also occur.
If what is
If
massless?
the hidden photon is massless,
Yes.
then this process will also occur.
Would this process occur? I think so, yes, but there's an important caveat that if it's massless, you can't actually tell the difference between it and the regular photon. So I think, so in that case, in that sense, no, it would not occur. Yeah.
There's one basis where you can write the interaction, but it has an explicit M in it.
And rotate it
that basis
away,
would see
yeah.
that when M equals 0, so.
If the hidden photon mass is 0, then we cannot distinguish.
Yeah, there's a hidden M dependence to this process.
Results can be different. Maybe. Results can be different.
What can we do?
Results of the U1
Charge.
will can be different. So we get two U1s with different results.
Yeah, that's
Like,
so
there are
if,
things which are charged under the dark U1, then yeah, you can have effect.
Yeah,
But if there are
exactly.
Only things charged under the normal U1.
if the interaction's only coming from this kinetic mixing, then if it's massless, it decouples. But you could add explicit charges under it, and then you would get it.
That is the linear combination dark couples is no more, and you just call it for.
Exactly,
Yeah.
yeah.
Then,
Yes.
then in that sense, there is no direct introduction to the dark.
So we can also think about this in the sort of propagation basis. And in this picture, what's happening is the electrons in your source, they directly couple to this hidden photon. So they can just produce it with some small probability. And then those hidden photons, they interact very weakly with the screen. So they're able to get through. And then with some small probability, they interact with your detector. So you have the same physics happening in both ways of thinking about it. So this is a good idea. So people are doing these experiments. That doesn't necessarily imply that they will do them, but they are doing them. And there's sort of three main categories. We can sort of classify the existing experiments and future experiments based on the source of the photons that's being used. So you have experiments in the radio, where my source is some resonant cavity that I've pumped full of radio photons. And I'm looking for these photons to mix and travel over and mix back and populate some other cavity that would normally be empty. These give you very, very nice bounds, a very nice reaches, and they cut off at a particular mass. All the limits from these cut off at a mass around 10 to minus 5 eV, which corresponds to the energy of a radio photon, a gigahertz photon in the source cavity. If you want to go to higher masses, you can use optical sources, use a more energetic source. So people have done that as well with the ALPS experiments, and those push you up to like an EV. And then I classify these as light shining through walls experiments as well. You can also use the sun as a source, and you essentially look for X-ray photon in the center of the sun to mix into a hidden photon, travel all the way to the Earth through some, crust into your cavern where xenon 1 ton is, and then it can mix back and be absorbed in the detector. So those give you very strong bounds that go all the way up to masses corresponding to the temperature of the sun.
For the sun case,
Yeah.
At least when people talk about this for axion, they don't really talk about it as light shining through walls because the production is like a pre-methodic process, right? Like,
Yeah.
if the statement that for hidden photons, it really is the same thing, because it's like mixing each other for axion, it's kind of different because of the different production.
Yeah, I guess so. I guess the point there is it's really, I mean, but the Primakov is kind of like, it's still like you're bremming a photon that mixes into the axion, right? So I would
Kind of,
still
I mean,
consider it.
Usually for light shining through walls, I think I need a magnetic field for the axion, because like it converts in a magnetic field. But it's
Yeah.
not really what's happening in the sun, but
That's correct. Yeah. I mean, it's the magnetic field of the Coulomb potential that it scatters off of that plays that role, I think. But yeah, I mean, either way, this is kind of playing word games. Yeah. In either case, you're getting production of this particle in the sun, and then you're shielding out the ordinary sunlight and protecting it on the other side. I think for the hidden photon, you're right that it's more directly analogous, that you're just thermally mixing.
So yeah, maybe with that one, so like you focus on that one, right?
Mhm.
The differences are in this production, you really have to increase some data or something. So that's the difference. So
Yeah, so for you could do, but all the physics I'm going to talk about would work just fine with an axion, except that you would need some background magnetic field to contribute the mixing, because it's the interaction is axion to photons. It's just, it happens that the results are not nearly as impressive for the axion. Basically, other constraints are much more significant. So the technique I'm going to describe wins a lot more for hidden photons than other things. So that's why it's the focus. Okay, good. So these are existing and future results. So, and you see this structure that they all kind of, segregate by energy scale, that at roughly the energy scale of radio sources, these are the radio experiments, and they cut off. Dark SRF is an important one to point out. This is an ongoing light shining through walls experiment using radio cavities at Fermilab, which is, these are the projected reaches, and this is the reach of their current kind of prototype experiment. And then you have a similar thing happening in optical, and a similar thing with the solar bounds. And so the sort of the lore of these experiments that has been understood before is that these right-hand wall here that's shutting off these constraints, this is a solid thing. This is a solid thing that you cannot move. And this is the perspective I want to challenge today. The xenon 1 ton is it's the xenon 1 ton dark matter detector, and they're looking for if the sun produced hidden photons, they would they could travel into xenon's box of xenon, convert back into a regular photon. These would be X-ray and be absorbed, and there'd be a signal. So this is just looking at they can set this exclusion just from their data.
So why sun? Because sun is larger, why not Jupiter only?
Yeah, because the sun is much brighter, produces a lot more photons. Yeah. It's the photon champion of the solar system.
Yeah, for all the sources are there, electrically uncharged sources, right? So may I ask a question about, so is it correct that all, people have a capability to make predictions for a portion of the power of the source, which is attributable to the dark hole?
Yeah.
Given this one?
Yeah.
Yeah.
It's roughly epsilon squared.
They know the charge and
Perhaps something before. Yeah, that's right. Yeah, so it's
because they know that the coupling in dark hole.
exactly, yeah, that's something you can compute. Yeah. And it's, so it goes like epsilon to the fourth. It's a very small amount of power, extra power that's in it. So That's why this technique is useful. You want to like shield out all the regular E and M power. So you have sort of a zero background to look for this small amount of extra power.
So if I understood well, the white, the region is the allowed region in
Yes.
parameter space. So you don't have any other physical constraints this model, because if there is such a light photon, maybe the lifetime of the sun is smaller, like action, where you have significant astrophysical constraints.
Yeah. So there are other constraints. I mean, I'm showing them all that fit on what's the plot that's shown here. But like, so the CMB,
This is okay, this is understood, but
this,
I mean, that's for the
that solar cooling one is.
it's this
here.
time. Okay.
So I colored this such that things that could be understood as light shining through walls are in the colors, and the grays are other types of bounds.
Okay.
Yeah, but for the sun, the like sort of the light shining through walls is stronger than the cooling limits.
Okay.
Okay, good. So the goal
Sorry,
here,
one more-
yes.
Sorry, and when you perform this experiment, do you assume the dark work is not dark?
Correct. This experiment
Yeah.
is agnostic to whether it could be dark matter or not. We're just interested, does this exist in the Lagrangian? So, I mean, if these limits apply to dark matter, because if it was dark matter, you could still make it in the lab. But even if it's not dark matter, if it's just in the Lagrangian. So if you include dark matter, then more constraints appear on the
Yeah.
plot.
Which will serve as noise or from the point of view this text. Like, dark, even if
Well, I don't
portion dark matter is
believe.
explained by dark photon, if that's the case, then still we have dark photon here and there.
Yeah, I don't believe
Serve as noise.
so, because as we'll see, like this is a resonant search where the drive is at one particular frequency. And so it's going to generate hidden photons regardless of their mass at that frequency. And so we tune the detector right to that frequency. So if they also happen to be dark matter, you would only have interference if the mass happens to align to a part in 10 to the -6. Yeah. So we're really like tuning in on the laboratory signal.
So photon are massive, so they travel in the speed of light, and dark photon in general, they're massive, so their speed is different. So does it mean if you have many dark photon in the universe, the light that is made are very fast transition, the speed of light? And the change in the speed is a function of epsilon and mass.
Yeah, something like that. That like the propagation of a photon is not trivial anymore. So like I'm understanding you right. That's essentially what these CMB bounds are saying, is that as light propagates to us, it's going to mix into the hidden photon, which then has a different phase velocity. So that tells you that like different frequencies of CMB travel at different speeds to get to us. And that mixes, so you no longer see a like thermal spectrum.
So the CMB has already put on the.
That effect, yeah. Early, I mean, one consequence of this would be that the CMB would now have wiggles in it. The spectrum would have wiggles that are not actually seen. So that's what that limit is. Yeah. Okay, so the goal of this talk is to really focus this sort of open space here, and to try to push this line over, right? This line is a real bummer, in part because these limits are so strong, right? That just slightly over here, you have no constraint from this technology. And so why is that line there? The basic lore is that this is a solid, this is some concrete constraint that you can't really move, and it's coming just from kinematics. That if this dotted is future experiments that are underway. I mean, these are both like funded things that are happening and taking data now.
Taking data.
Mhm. Yeah. Yeah, and then the colored ones are existing limits. And the basic idea here is just, your intuition from particle colliders or whatever, that, you're producing these hidden photons. And so if they have a mass, you need to have enough energy in your source to be bigger than that mass to produce them. And so if you have a radio cavity, you're not going to be producing things that are much more massive than radio energies. But that's a little too quick. We know, for example, that that's not quite true, right? In particle physics, all the time, we produce, virtual particles who have energies possibly much less than their mass. Produce is maybe not the right word, but we see their effects very clearly. And so something like this should certainly be possible, that we can produce like a virtual hidden photon from this source, even if it's very massive, and get some effect from that. So the way I like to think about this, even though, as Sarif mentioned, I'm part of the SQMS collaboration, in my heart, I'm a classical guy. And so I like to think about this in classical language. If we take a wave equation, here's just a dispersive classical wave equation, the same equation that the hidden photon field will obey. This equation has a particle-like dispersion. And if we drive a signal at a frequency omega much bigger than the mass, this looks like, a massless or approximately massless waves. But we know that this solution works even if the frequency is much less than the mass, right? This solution, this plane wave, works for any k that obeys this. And if we take omega to be much less than the mass, then k is valid, it's just imaginary. And then this becomes, instead of an oscillatory solution, an exponential solution. So these are what are called evanescent modes. And we're familiar with them from, they show up all over optics and acoustics. And this is the same math as quantum tunneling, right? So if the mass of our hidden photon is much, much bigger than the source, then we will still be able to produce hidden photon modes, disturbances in the hidden photon field. They'll just be exponentially decaying modes instead of propagating modes. And you might think, so what, like, how does that really help? If these things are decaying over some very short length scale, doesn't that, mean that we need to now bring our detector that close to the source, like compress this whole experiment? That's not really very feasible. And the key point that I want to convince you of is that no, you don't need to do that. So here's a good way to sort of think about it in a cartoon level. If we are now in a evanescent regime where the mass of the hidden photon is much bigger than the frequency, then I should think of each of these, propagations as coming along with some evanescence suppression factor, where d is just the distance the hidden photon has propagated. And when I think about it in this basis, we can ask, how far does the hidden photon actually have to propagate in real space in order to produce a signal, right? It doesn't have to go from here all the way here. It only has to go across the barrier. So the real length scale that's going to set the exponential suppression is the thickness of the barrier. Right.
So you also have this size zero, right? In the previous expression, you also have this size zero.
Yeah,
and,
like the amplitude.
Yeah, the amplitude of the dark photon or this one photon. And you don't have any suppression there. I mean, if there's a mismatch between the frequency and mass, I understand that you probably will be part of the exponential suppress, but
You do, yeah. Like when we do the calculation for real, there's additional, exactly, there's additional power law factors in mass that,
but it's not exponential.
yeah, not exponential. Like another one that shows up here is if this distance, if the source to detector distance is really long and the thickness of the barrier is really small, and the range of this dark photon 1/m is just a little bit bigger than the barrier, then we sort of lose out on all of the possible conversions that happen on the way. And you're only sensitive to the conversions that happen like right here and then right here. So there's sort of a volume suppression that you get there from, so there's various suppressions of M that show up. But the key point is the only exponential suppression that will appear is the thickness of the barrier. Yeah. And effectively, all the previous experiments I've talked about are effectively thick barrier experiments. They're experiments where the barrier is very large compared to the frequency, to the wavelength of the light being used. So those experiments, as soon as you hit the evanescent regime, they just shut off. Did you have a question or?
No, that's not the one to understand what, because like now you can, let me say you write, etc., you write equation. How do you parameterize the wall? I mean, how dark is the wall? Because has some dielectric properties, right?
Yeah, good. So I'll get
So, I
to,
mean, what is the parameters of the wall?
yeah, so the wall that we'll envision is a superconductor.
Okay,
And so there is the darkness of the wall is, there's some finite penetration depth of real photons
yes.
into the wall. And
So
so,
the electric, let me say, constant of this wall, I mean, if some, significant what?
I don't know, but the dielectric constant of the
Because in order
superconductor
to solve the
is,
equations,
yeah.
in
I mean,
the
the way-
propagation of the wave, you have to know the,
Yeah,
you know.
the way we
its place.
treat it is we treat it as like a finite conductor with some finite penetration depth.
It's contractor,
Yeah, conductor.
it's a contractor.
Yeah.
So how can you think about this in terms of the propagation?
Again, we need to solve the equation, right?
Yes, very good question. So, right, it's time for two things, right? The propagation basis, because in the propagation basis, it seems like we are indeed propagating from here all the way to here, right? But there's a subtlety you're missing in that picture, which is that in the propagation basis, when the fields encounter this barrier, something interesting will happen. So we'll see that now. And also, yeah, it's time for some math. So let's be serious physicists and let's do some math.
Can I actually ask one question related to the previous picture?
Yeah.
If you really want the conversion here to happen like right before and right after the plate.
Yeah.
Right? Could you do something like put like dielectrics there to try to get some like resonant conversion, get the like plasma mass of the photon to match the.
Probably. Yeah, I hadn't.
He said it's contractor, one thing that.
Yeah, I'm saying like
add-
outside, like
add
outside, like a layer on top of.
Possibly, yeah, possibly. I hadn't really thought. I mean, it is true that a simpler version of that is you do better by like making these as close to the wall as you can. Like, so we sort of
Yeah.
try to minimize that wasted space. But yeah, that's a good point. Okay. Good. So let's be serious, but not too serious. Okay, this is a toy model. This is a question I want to ask. Suppose we have a sheet of current, right? A nice simple toy model. We have a planar AC sheet current. We know what would happen in ordinary E&M. This would radiate some plane wave. And now let's put our wall here. Let's take a conducting sheet. Infinitely thin, perfect conductor right here. We know what would happen in E&M. If there's a current K here, a screening current would appear, whose magnitude is also K. And it would screen out any fields from appearing back there, right? This is how a mirror works. And so I want to ask, how does this change? How does this change if we add a hidden photon? Do we get some field over here if we add a hidden photon? And particularly, let's add a very evanescent hidden photon. So let's add a hidden photon whose mass is way bigger than this frequency. And 1 over the mass is way smaller than this distance, and also the distance to where we will put our light detector, electric field sensor. So we can work through this. We need the field equations. So we can get those most easily from the Lagrangian in the propagation basis, because then the two fields just decouple. And so we have ordinary Maxwell, and this gives us Maxwell's equations here in blue. And then we have the Proctor-Lagrangian here, and this gives us a massive version of Maxwell's equations. They look exactly the same, except with the mass, and our coupling to photons is now, coupling to charges is suppressed by epsilon. So this is sort of half of Maxwell's equation, or not half of Maxwell's equation, this is half of E&M, right? We have how, this is telling us how the fields respond to charges. We need the other part as well. So the Lorentz force follows just from this coupling of current to field. But we notice that we have the exact same structure over here. So really the current couples to A plus epsilon A prime, couples to that combination. So from that, it follows that the Lorentz force is going to look like this. The Lorentz force has the ordinary form. It just couples to these particular linear combinations. It will also follow from there that conducting boundary conditions, like how does a conductor, what demands does a conductor make on the field, they apply to this linear combination. Okay, so don't want to make things too, complicated, but this just cries out for me. Right? You can't just let this linear combination sit there without giving it a special name. We have that this particular combination is the thing that applies forces to a charge. And it would follow that the orthogonal linear combination doesn't apply a force. Like if you have fields existing in the orthogonal combination, charges don't care. They don't respond to it. So it will be useful to give these things names. The visible field, which is this combination, and the invisible field, which is that combination. And we can write everything in terms of the visible and invisible fields. And then our interactions with charges and conductors are very simple. The visible field just behaves like an ordinary Maxwell field, but now your field equations are coupled together, right? These visible and invisibles are not propagation eigenstates. So your field equations are coupled. They would mix into each other when they propagate in free space. So these will be handy for us to have. So now let's solve this toy model. What are the fields produced by a current? A sheet current. Well, we get, now thinking of the propagation field and the propagation basis. This thing just sources both types of fields. They're the massless one and the massive one. So the massless one is the ordinary thing. We get some plane wave that propagates that way. And then for the primed massive field, we get, you just go back and solve it to get these very three factors, but you get a evanescent mole, right? Okay, we're taking the approximation that M is really big, so you get some decaying evanescent molecule. So these fields are going to impinge upon the conductor over here. And what's going to happen? The conductor will demand that this visible linear combination goes to zero at a surface. Right? The conductor will generate some screening current, demand that this goes to zero. The only way it can do that is by adjusting the value of this screening current, which will produce its own E and E prime fields to cancel out these on the surface. And the important point is that the conductor doesn't care about E or E prime individually, separately. It only cares about this linear combination.
May I ask a very simple and very naive question, because I'm a little bit confused, okay, right? If you write down massive electrodynamics, as you do, for example, the Gauss law does not apply anymore.
Right.
So, okay, I'm gonna look, but in order, let me say, to apply the usual, as you do maybe, boundary conditions in the usual electrodynamics, this is not maybe, I don't know how figure it is.
Yeah. So you could go through the it's a good question.
I mean, even in the conductor, you say the electric field is zero, right? This I can understand in electrodynamics, because this is really a result of the Gauss law. Inside the conductor, right?
Yeah.
So, okay, there's no way to have a electric field.
Yeah, so you
If
can,
the Gauss law does not apply this, I don't know how I mean, maybe this is not zero, maybe it's different from zero.
Good, you're right, it's not obvious, but this is the right thing. So you can go through the exercise of like, you get Maxwell's equations and you analyze them like in infinitesimal surfaces around a boundary.
Okay.
Like you will still get from,
Maybe the answer is in the previous transparency, you had, I mean, you wrote that, okay, it's a mandatory constraint. This thing, this,
oh yeah,
maybe this is related, but
I think
but
it is.
you force this to, because this is the gauge fixing.
Yeah, so
And from this, you can get something similar to the Gauss law.
you do, so yeah, when you can break this up into like the vector component equations, like Maxwell's equations,
Yeah.
you get something that's similar to Gauss's law, but it has an extra term in it that makes it different than Gauss's law.
Yes.
So you can still use it in the
Because
same
this
way.
equation at the end of the day is that the time derivative of the vector potential plus the d of A equals to zero. If you are in the start limit, let's say, the first is zero and then the other is zero, okay, I don't know how you play this game. Just because I just want to understand how you get the boundary condition, that's it.
I think the answer to your question is that E parallel equals to zero.
Yeah.
That doesn't come from Gauss's law, that comes from Faraday's law. It's the like curl.
Still is related to this gauge fixing law.
Yeah,
No.
Well, I
No,
mean,
but-
you need to use this to get Faraday's
Yeah.
law
Yeah.
from here. Yeah,
Yes.
and this is actually not a like, something interesting about this case is you don't have the gauge redundancy when you have the mass.
Mhm.
So when you work out the field equations from here, like this isn't a choice, this is something that
Yeah.
Just
Okay.
has to be.
Okay.
satisfied.
Okay. Thank you.
But Faraday's law still applies, even in the massive. You're right, Gauss's law changes, but Faraday's law.
That is right, yeah, that is right.
I think Faraday is kind of from the outside,
Yeah.
which is why. I was-
That's right, yeah. Okay, good. So the conductor tries to enforce this boundary condition, this condition that the visible field goes to zero. So what we want to ask is, we want to compute this screening current. We want to ask, what is the visible field impinging on here? And in this case that they're far separated, the visible field nominally has components from both the massless and the massive fields. The massive component is going to die off long before it reaches here. So what's hitting here is essentially just this massless plane wave component. But when the conductor goes to screen it, it's going to generate both components. It's going to generate the massless E and the massive E prime. It doesn't have a choice. They both couple to the current. It generates both of them. And so the current right here at the surface, or excuse me, the field right here at the surface, which is within the like fall off length, the 1/m. So we don't have the exponential suppression. Looks like this. You have a contribution from E, a contribution from E prime. And so it follows that for this to cancel this, Ks can't equal K in magnitude. It has to be slightly smaller. So you find that the screening current that you need to satisfy boundary conditions is slightly smaller than the source current. They don't match up perfectly anymore. And that means if you now step far away over here and ask what fields you observe, if I'm sufficiently far away, I'm not going to get any of the massive components reaching me. The visible field that I see far away is just the plane wave component from here and the massive plane wave from here. And if epsilon was zero, these things would be equal and opposite and cancel, but they no longer cancel now in this picture. Or in this scenario, they no longer cancel, and the sort of degree, the amount that's left over scales like epsilon squared. So you have this mass, the massive mode, the evanescent mode gets to participate in screening here. but it drops out over here and that spoils the screen over here. And so you have some visible field that remains at some far distance away. And you can sort of see from this picture that, like, as I make these distances very, very far, nothing is going to change here, right? This is the limit of far separations. So there's no suppression coming from this long distance. Okay, good. So let me, in the interest,
You are saying that this one is really just increasing or something.
yeah. Mhm. Which is why there's no exponential suppression showing up at all over here. So what is sort of happening here on a higher level, and so you know, in this propagation picture, what is happening? The physics here, the sort of fundamental physics that's happening is the same as in neutrino mixing or any sort of mixing. What's different is we don't have the oscillatory nature of the mixing. Instead, it's an exponential type behavior. So what happens is we generate some visible field. The visible field is not a propagation eigenstate. So as it propagates towards the shield, it mixes into some admixture of visible and invisible. Like if it was a neutrino and it kept on going, it would eventually mix back, right? But we don't get that. This is not, that's what's different here. This mixing is sort of a one-way process. It looks just like you've taken the trig functions in neutrino mixing formulas and replace them with hyperbolic functions. It's the same sort of behavior. When you get to the shield, what does the shield do? The shield shuts off the visible component, but it allows the invisible to pass through. Then you would normally not be able to detect the invisible, but it's not a propagation eigenstate. So as it propagates, it mixes back into some visible component. And that's what you can detect. So that basic structure is the exact same thing that happens in other mixing processes. The difference here is we just have this exponential sort of behavior as opposed to oscillatory behavior. Good. So let's remedy this fact that we've taken the wall to be really thin. What happens if the wall is thick? That's not an approximation we can get away with because we want to think about, you know, building an experiment that probes really, really high masses. And as we consider bigger and bigger masses, eventually the range 1/m would resolve the size of the wall. So we need to think about what happens if 1/m is smaller than the wall thickness. And this is fairly straightforward to understand. Again, the basic picture is we would have impinging on our wall some visible and invisible components of the field. And we want to ask what field components propagate inside the conducting barrier. And that's straightforward to solve. What does the conductor do? If it's an ideal conductor, it shuts off the visible component. It sort of zeroes it out. So we don't have two propagating modes inside the conductor, we only have one. And if we go back to our field equations for the visible and invisible pieces, there, you know, this coupled thing in free space, but in a conductor, the visible components are shorted out, and now they're simply solved. You see that inside a conductor, the invisible is a propagation eigenstate, and it just has some mass. So what happens here is this guy will be shut off. This guy will be allowed to come inside, and then it's going to propagate just as an perfect evanescent mode inside. So it will be decaying exponentially. And so when it leaves the other side, its amplitude is suppressed, and now it's going to mix back into the visible, just like before, which inherits the suppression. And you can actually go through it. You could do this exactly, and you see this exponential suppression appear in the barrier thickness, just like what you would have guessed would happen. Okay. So this is the basic physics. So now let's think about how we would turn this into an experiment. So this is the experiment that we proposed. We're going to do a radio frequency cavity type experiment, but we're now going to place the cavities as close together as possible with a thin superconducting barrier in between. We'll drive this with as much power as we can manage. and we'll look for a signal to appear over here due to evanescent modes crossing the barrier. So there's a couple sort of practical concerns we should address. The first is, how high of masses can we reach with this technique, right? How high of masses can we get to? That's equivalent to saying how thin of a barrier can we tolerate, right? So there's challenges with a thin barrier. There's a fundamental issue, which is that the visible field is not shut off instantaneously on the surface. There is some penetration depth. And so what we want is that the barrier is thick enough to shield out all of the visible components, or at least much more of it than our signal. So we're going to think about a superconducting barrier. So the penetration depth in the superconductor is called the London depth. And so the condition we have, the sort of minimal condition on the thickness, is that the suppression from the London depth, we want that to be much stronger than the expected size of the signal. And so here we're saved by two things. One, even though we're going to probe epsilons that are very, very small, this is exponential. So we don't need that many London depths of material to get strong suppression. And two, the London depth of the superconductor happens to be very small. So if we apply this condition, we find that for the epsilons that we can reach, we need about 50 London depths, which corresponds to about 3 microns of material. So that's not much material at all. And 3 microns corresponds to a mass of close to 0.1 V, which is about 4 orders of magnitude improvement over the existing thick walled experiments.
In this, let me say, Jason, I mean, that you still you want to have D much bigger than MA, right? The mass of the photon, right? Or no? I mean, this is the
No, so D is
much bigger than MA to the -1.
the other way around. That's the case that'll be suppressed.
Ah,
So M much less than 1 over D
okay.
is what we will be able, where we'll have this signal.
Ah.
So we want D to be as small as possible to push our boundary up. But if it's too small, there's going to be
So this is the upper bound. So this is
upper bound of the mass we can probe. That's right. So there's other sort of practical concerns. One is that a thin barrier doesn't conduct heat very well. So there's a conductor right here. There's still some ohmic heating due to this field right next to the conductor. That heat needs to get out to the outside of the system where there's going to be, liquid helium to cool it. And since that heat has to flow through a thin barrier, the temperature in here is going to be hotter than the temperature here. And we can't let that get too hot to spoil superconductivity. That will limit things. You could also be concerned about it's a flimsy little thing, and there's a lot of electromagnetic power there. Will the radiation pressure start flapping it around and break it? So one basic solution to both of these, for one, is they don't. These are not really concerns for sort of medium-sized barriers of order like 0.1 millimeter or so, which still gives us an interesting experiment. But if we want to push to the fundamental limit, we can need to solve these problems. One approach is to add a substrate here. The idea is to make the barrier mechanically and thermally thick, but not electrically thick. So we can put a dielectric here, which doesn't screen fields, but it will allow heat flow. It will provide stability, and then we plate onto it a thin layer of superconductor to do the actual screen. And plating superconductors onto dielectrics, that's an established technology. This would have the trade-off that the acute quality factor over here gets hurt by the sapphire, but it's a trade-off that you just live with. And then there's other more sort of exotic ways of possibly getting around this. So let me quickly go through how we calculate the signal for real in this experiment. Something interesting that we ran into is that, the calculational formalisms that previous experiments have used, they do include the evanescent modes. Like, so normally we can just take those formalisms and apply it to our setup. The evanescent modes are included just by default, right? When you solve Maxwell's equations, they're there. The thing that was missing in previous experiments was not the formalism, but that the geometry had a thick wall, so that squashed that signal. But we actually found an interesting effect when you apply those formalisms in the evanescent limit. They become very unwieldy, and there's like some not intuitive cancellations that happen that make it very surprising. So we developed a different way of going about the calculation that sort of makes the qualitative behavior in the evanescent case very transparent. So let me just briefly run through that. The idea is to say, start kind of work backwards. So we have some receiver cavity, and next to it is going to be some emitter cavity, which is driven with field. So there's some field inside here, and there's currents flowing on the walls. We ask, well, what signal appears in here? That signal is governed by this equation. This is just follows from those previous field equations that I've written down. This looks like just the ordinary wave equation for the visible field with this additional term in it. So we can identify this term as like an effective current. And then the physics of how does a current inside of a cavity generate cavity modes? That's a well understood thing. We can apply that understanding. We just need to figure out what this effective current is. The effective current is given by the A prime field that's generated, sourced by this cavity. So we ask what sort of A prime is this emitter source over here, and then we use that to do this calculation. So how do we get that A prime field? This is where we differ from previous work. The A prime field, we're working in the propagation basis, where A prime is sourced by electromagnetic currents. So we can get the A prime field by just integrating the Green's function of the currents on the surface here. So we do some surface integral over the emitter cavity to get the A prime field. And this integral in the evanescent limit is actually very easy to just estimate, because the propagator in the Green's function is this exponential suppression. So if I want to ask, like, what is the current, what is the effective current here? The only part of the integral that really contributes is this closest piece right here. So that simplifies the integral. And we get this nice result that the A prime field, and equivalently the effective current that lives over here, always tracks. It just mirrors the structure of the real honest to God electron current on the other side of the wall. So it has the exact same shape, same direction, and it always follows parallel to the surface, which is an important detail when it comes to actually designing this experiment.
The calculation on this slide is in the propagation basis. But on the previous slide,
Yeah,
it would have been in the like.
we're kind of mixing in a way that should make you uncomfortable, but it's okay. Basically, like this, the point is that the visible,
I guess it's like you only care about A prime and order epsilon or something.
there's something,
Order
yeah,
epsilon,
so you
they're
can, that's right. That's right. It's also the fact that it's like, this is just a source for the visible field. So it's just the fact that the propagation field sources the visible field. You could write this in terms of visible and invisible, and then you have extra epsilons. But so this is an exact calculation of that. This is just looking at the white here is the emitter cavity. This is the longitudinal direction. This is the radial direction. And for two different structures of modes inside the emitter, this is the structure of effective currents that you get outside. And the point here is just that again, the directions here are always perpendicular, parallel to this surface. Okay, so.
Is the geometry here like they're separate cylinders?
So this is just looking at one emitter and then the same emitter in a different mode. And then we could place a detector anywhere you want around there. We place a detector anywhere you want, and then pick the mode structure that aligns with J effective best for where we placed it. So we would naively, like the setup we imagine is placing another cavity right here. Okay, so let me just kind of skip through this. Once we have J effective, we can now compute what the signal will be rung up in the detector cavity. So from there, we can get parametrically what is the expected signal in terms of cavity geometry parameters and the fundamental physics parameters as well. So a couple interesting things is we do have some power loss suppressions in amp. So as we go to higher amp, this does get worse in a power law fashion. And then what's also interesting, if you're familiar with cavity experiments, is this doesn't scale with the volume. Usually these things scale proportional to the volume. Now we have this more complicated shape. So fixed volume, we do better if the cavities are more. So we imagine doing this experiment in kind of 3 stages. So this is a picture of the dark SRF experiment that's ongoing right now. Here's emitter and source. Maybe this is emitter and this is source, I don't remember. But the wall in this case is this like 10-centimeter gap in between. So we would imagine doing this experiment, but instead moving these cavities really close to each other. And we're going to kind of consider sort of 3 qualitative stages. The first is what can we do with like existing cavities that you would find in the closets in the lab doing this experiment with a fairly thick wall that's thin enough to do something interesting, but not so challenging to work with. Now this experiment is ongoing and they plan, they project to make a lot of improvements to their readout technology, their cavities. So we can imagine just piggybacking off of that, like how much better would we do if we did this again using their like projected improved setups. And then, the ultimate is to take that projected improvements and optimize it specifically for the thin wall case. So take a pancake geometry, take a thin wall, imagine we solve whatever problems we need. This would be sort of the best limit we could conceive of. And this is what we do. So the sort of current technology will allow us to reach this little bit of space here. So this is that same plot I showed before, where this is the dark SRF projection. These are the solar limits. I've just zoomed in on that triangle. If we take all of dark SRF's improvements, can consider adding those, we can push all the way down here. And it's not surprising that they sort of line up here, right? We're taking the same basic parameters. But this allows us to kind of just fill in this space. And then if we consider the like very thin wall pancake cavity, that the pancakeness pushes the resonant frequency over. So it peaks over here, and then we can push the ball off over, all the way up to near 0.1. Okay. So let me wrap up. So let me just say briefly, the idea here is that the mass reach in a light shining through walls experiment is fundamentally given by the barrier thickness. And so we can take advantage of that by using very thin, electrically, solid barriers. We can use radio frequency technology to push these experiments to much higher masses, where they significantly outperform the optical experiments and will give us the best reach for any terrestrial experiment up to about 0.1 eV, masses of 0.1 eV. And then I went over this part rather quickly because it's kind of technical, but we've also worked out like the best formalism for calculating these to really characterize sort of the qualitative features of these signals which are a little different than other light shining through walls signals. So you have to make some, specific design choices to really optimize this properly. And then this work is under development by the Dark SRF folks for future work in their experiment. So, thank you.
Do you have any more questions for that?
What is the budget of this experiment related to an idea?
That's above my pay grade. No, I don't know, it's a small scale experiment, like a few million, I would think. Like this is, you need to build these cavities, but a lot of them are already built and laying around. I think running the cooling is probably the most expensive part, like keeping this, keeping all of this surface cool down to a few Kelvin temperatures. I think that's probably the biggest expense. Yeah.
In this region of the parameter space, how this, let's say, experiment competes with other experiments?
Yeah, so the only other planned experiment in this space is way up here. This ALPS 2. And so we're talking about right there. Yeah.
Some other experiments I could some qubits, blah blah blah.
Mm-hmm.
Is in this region for
I'm not familiar. I'm familiar with some
more Roy mentioned
some dark matter experiments
Yeah.
using
Uh.
qubits where the dark matter
yeah.
excites. I mean, I don't know what masses those are. They're more to EV masses, I think.
I look on more papers.
But I mean, I believe those are also dark matter specific limits where this would be more general.
Okay.
Oh, okay, here you're not plotting on dark matter.
I'm not plotting any dark matter limits. Yeah, this is strictly just, does this exist?
But applies to just not.
Right, yeah.
Yeah, but if you added dark matter experiments, then you'd probably have all the cavity tables go.
Oh, this is a good point. Yeah. If you add dark matter experiments, like things like bread, if you're familiar with the experiment bread, they're a big optical dish where hidden photon dark matter can convert and reflect off the dish and be focused on the little detector. They push down below. They push down here in similar mass range.
I see.
So they're much better, but that's specifically assuming it's dark matter and they have a great big dish to collect a lot of dark matter and focus it down.
Okay.
Yeah,
So
so
they're more expensive experiments too, actually.
yeah, that's a really big experiment. Yeah, if it's dark matter, then you can use that to your advantage to design a more more sensitive experiment. I think that's just generally true of dark matter searches versus a new particle search.
Have you guys talked at all about ALPS 2 about how they might be able to implement it? They have a wall.
Yeah, I haven't talked to them about it. No, I haven't. I mean, what it would do is it would take this from a straight line to some thing like that, which is already ruled out, but it would be. I don't know if it's harder as well to get.
Yeah, and but also already without, no?
Yeah.
Right,
They're already, yeah. I mean, it's going, though, to be fair, the ALPS 2 does much better relative to these other experiments in the search for axions. That's really what it's designed for, because there you get an enhancement due to the magnetic field that they apply. So they're not great for hidden photons, but they shouldn't be judged just on that. It's really an axion experiment.
Based on photons.
So I don't know the historical development, but in their like,
Kind of feel like I should know, because I was on busy.
in their latest documentation, they say A stands for any. It's the any light particle search.
Okay.
I got it. So I guess actually in that case, or even for you guys, if you wanted to do an axion version,
Mhm.
like if you want to turn on a magnetic field, big magnetic field, you can't use superconductors, right?
Yeah, the best axion version that I could think of would be, there's an axion search idea by Ronnie Harnick and Christina Gao. That's, you don't have a background magnetic field. Instead, you take two cavities and you drive two different modes in the emitter. And those two modes have an E dot B, so they can source an axion, which would then mix in the, you then would also drive a mode in the detector and it mixes into a fourth mode.
Okay,
So you could do that sort of search. In that case, you could do that with a thin ball and it would improve. In that case, the limits are only a little bit better than solar cooling limits anyway, and this kind of buys you just a small little corner of parameter space. So it's, I mean, the mode's impressive here, but you could do it with that sort of search too.
I guess I was gonna ask if Alps wanted to put a thin wall, but still use a magnetic field.
Oh,
What's like the shortest penetration depth you can get with not a superconductor?
I don't know. But they could also make it, they could use a superconductor because. Well. No, I
We want it to
think,
get
no,
very
they
near
would
the
need,
wall,
yeah,
right?
it needs to be very near the wall, so that would
Yeah.
be. I think they also, there's a problem in that the. Here we have an advantage, there's a big hierarchy in that we can get a wall that's much smaller than the wavelength. Like. They can't, there your wavelengths are like micron size.
Oh, yeah.
So sort of as soon as you go to the evanescent limit, you're already at the like thickness of the walls.
Yeah, yeah.
So I don't think it. I don't think you can make walls much thinner than that, and then it really doesn't buy you that much. Like here, we're able to move the cutoff orders of magnitude, and we're able to move the cutoff. by some magnitude.
So does this non-known length, does it also depend on the frequency of the photon that you're shooting? Because I assume that obviously you're shooting a higher frequency photon.
Yeah, the penetration depth depends on frequency. Yeah, I'm not sure what the like optical.
So I kind of guess that like, the frequency is kind of higher than they can penetrate.
Maybe.
And then-
I think it's more complicated. It's more complicated because I know that like in radio, lower frequencies can penetrate better in some. That's why like governments use these extremely low frequency emitters to communicate to submarines.
Yeah.
Because really low frequencies penetrate seawater, but typical radio frequencies
Yeah,
don't.
I agree thinking that, in the office, there's also the like signal discharge. To make the
Yeah. Yeah, I'm not sure. I'm not sure.
There are no more questions. Thank you again. And we will be going.